Hello students, welcome back. Let us resume our discussion in section 1. Previously, we were doing this example problem, remember? Cosine is 3/4. So, horizontal over hypotenuse is 3/4. We want to find out the vertical, and we can use Pythagorean theorem to do that. 3 squared plus y squared is 4 squared, the hypotenuse. So y squared is 16 minus 9, so we get 7. Taking the square root, y is square root of 7. So I know all the sides, so we can find out all trig values here. Sine is square root of 7 over 4, opposite over hypotenuse. Cosine is 3/4. Tangent is square root of 7 over 3, opposite over adjacent, and so on, the reciprocals. Even when these numbers are different, you can use the same arguments to answer everything actually. Just use the Pythagorean rule. Now let's go to the next problem here. This one's new. Solve this right triangle. What do you mean by solving a triangle? That means find out all sides and all angles. This is a right triangle here, so 90 degree here, 30 degree here. This one has to be 60 degrees. So the key points, finding A and B. How do you find those out? Well, we can use trig ratios. So if you use sine, then that's opposite over hypotenuse. So B is 12 times sine of 30 degrees. And then if you punch into calculator, what is sine of 30 degrees? You're going to get 0.5. So this is going to be precisely 6. So sine of 30 degrees, use your calculator, you're going to get precisely 0.5. Why is it so precise? Well, we'll figure it out a little bit later. Cosine of 30 degrees, this one is not that precise. Adjacent over hypotenuse. So A is 12 times cosine of 30 degrees. And this is going to be 12 times. And what is cosine of 30 degrees? If you punch it the calculator, you'll figure it out. If you do that, you're going to get 0.86 something. Yeah, that's what I got when you use my calculator. This turned out to be 0.866 something, and then in the end we get something like this. Is there any way to do it precisely? Actually there is, but that'll have to wait. For now, let's just be satisfied with these. Alright? With the angles, with trig ratios, we can figure out the sides, and vice versa. Speaking of doing things precisely, let's before that, let's take care of one more thing, which is still a review from high school geometry. Yeah, I remember helping these to many high school students, so I remember this. Trigonometry of complementary angles. The only change here, compared with high school geometry, is that it's written in radian measure. In degree measure, it's like this. So we have a right triangle here. And this is right angle. And this is angle A. And here's angle B. And then this is right triangle, and then internal angles must add up to 180 degrees, 90 degree already here. So the key point here is to make this observation. Angle A plus angle B, this value add up to 90 degrees. So how do you get B from A? of course, is 90 minus A. And how do you get A from B? Again, 90 minus B. So that's how the complementary angles are related. And in that case, let's make another important observation. Adjacent of A becomes opposite of B. Opposite of A is adjacent of B. So opposite and adjacent flip-flop. So cosine is adjacent over hypotenuse for one angle, and that'll flip-flop to opposite over hypotenuse of the other angle, the complementary angle, and so on. So we have sine becomes cosine, cosine becomes sine, tangent becomes cotangent, cotangent becomes tangent, secant becomes cosecant, cosecant becomes cotangent. Really, these trig functions and cotrig functions are related by complementary angles like this. It all comes from this, and then, of course, even more importantly, this picture. Opposite and adjacent flip-flops. Here, I wrote this in radian expression, pi over 2 minus theta, rather than 90 degree minus degree angle, but the idea is the same. And alpha plus beta add up to pi over 2. So sine and cosine, tangent and cotangent, and also secant and cosecant flip-flop. Alright, maybe not these two, but for sine and cosine flip-flopping, I know for a fact that you already went through this in high school geometry. Now, shall we go to something new? 1.4 is also partly covered in high school geometry, but I'll assume this is new. From this point on, I'll assume everything's new. So we're going to consider two humongously important triangles. Triangle number 1 here, 1 square root of 3, 2 triangle, or 30, 60, 90 triangle, or pi over 6, pi over 3, pi over 2 triangle. And triangle number 2, 1 square root of 2 triangle. This is an isosceles triangle, right? Isosceles triangle. And this one is actually coming from an equilateral triangle. We begin with an equilateral triangle with sides 2, and then take a bisector of one angle so that this divide bisects 30 degree, 30 degree. And this bisector of this top angle bisects the bottom side, the opposite side, perpendicularly. So 1 unit, 2 units, and then in the middle, by Pythagorean, you can get square root of 3, you see? Y squared is 1 squared, no, hypotenuse 2 squared minus 1 squared, which is 3. So if you take square root, you're going to get y is square root of 3, right? That's what we have here, square root of 3. And just looking at either blue triangle or pink triangle, you get a right triangle, 30, 60, 90 degree, and pi over 6, pi over 3, pi over 2. 1 square root of 3, 2 triangle. This is triangle number 1 of this course. Here's a triangle number 2, 45, 45 degrees, 90 degrees, so it's an isosceles triangle. And this is 1 squared plus 1 squared is 2, so square root of 2 there. So how do we utilize these? Well, we utilize those to get trig values of basic angles. Here's a summary. How to get these? Well, alright, let's begin with 0 degrees. So we have a triangle like this. Hey, you call this triangle? Yes, it is, sort of. It became so flat, it became a line segment, or degenerate triangle, you can call. So, vertical is 0, and horizontal is same as the radius. That's how this special case works. So sine of 0 is 0 over r, so 0. Vertical is 0. Cosine of 0 is r over r, so it's 1. Tangent of 0 degrees is 0 over r, 0 over x. Yeah, okay, x is equal to r, so it's 0. Let me show you another degenerate triangle, this time 90 degree, or pi over 2 in radian measure. It's this triangle. Again, the triangle became so thin, so tall, so it became a degenerate triangle, a line segment. This time horizontal is 0, so x is 0, so cosine of pi over 2 is 0. And then x is 0, horizontal is 0, so vertical became the same as radius, so sine of pi over 2 is r over r, so that's 1. And the most interesting of all is tangent. Tangent is undefined because denominator is 0, horizontal is 0. So tangent value gets very, very large as we get close to pi over 2, and at pi over 2 it blows off to infinity. As for the other basic values, alright, let's inscribe the triangle number 1, 30 degree, 60 degree, 90 degree triangle. 30 degree goes to the origin, and what you have, sine of pi over 6, 30 degrees, is y over r. It's 1 over 2, opposite of hypotenuse. Cosine of pi over 6 is square root of 3 over 2, adjacent of hypotenuse. Tangent of pi over 6 is 1 over square root of 3, opposite of adjacent. All coming from the triangle number 1. 30, 60, 90 triangle. We can utilize this again for pi over 6, this time positioned like this at 60 degrees there, or pi over 6. Sine of pi over 3 is opposite over hypotenuse, square root of 3 over 2. Cosine of pi over 3 is 1 over 2, adjacent of hypotenuse. And tangent of pi over 3 is square root of 3 over 1, opposite over adjacent. All coming from inscribing this triangle number 1 in the right place like this. The angle in question goes to the origin, and the right angle goes to the x-axis. Finally, 45 degrees, that's when we put triangle number 2 in there. So 45 degrees here, pi over 4, and x and y are both 1 to 1. And then hypotenuse is by Pythagorean, square root of 2. So sine of pi over 4 is 1 over square root of 2. Cosine of pi over 4, again 1 over square root of 2. And then tangent of pi over 4 is 1 over 1. And that's it. We get all the basic angles like this, and here's a summary. Oh, as for this 1 over square root of 2, you can multiply square root of 2 to both numerator and denominator, and you can rationalize like this, square root of 2 over 2, if you want to. I don't rationalize, but if you prefer, you can go ahead. And then 1 over square root of 3, again, you can rationalize, multiply square root of 3 to both numerator and denominator, and express it as square root of 3 over 3. So, sine of pi over 4, 45 degrees. Cosine of pi over 4, 45 degrees. You can express those as 1 over square root of 2, or square root of 2 over 2, either way. And then tangent of pi over 6, you can express it as 1 over square root of 3, or square root of 3 over 3. Either way, it'll work out. Me personally, I don't rationalize. I don't mind having square root in the denominator, so I like it this way. But most of the trig diagrams rationalize. Okay, alright, so much for 1.5. And in the next video, we'll come back and discuss 1.6. What kind of applications can we think of? Stay tuned, please.